This tutorial focuses on analyzing test questions pertaining to capacitors. What is a capacitor? As shown in the first diagram, any two conductors separated by an insulator or a vacuum form a capacitor. But in most practical applications, initially each conductor has zero net charge, and the electrons are transferred from one conductor to the other during charging. Okay, as shown in the second diagram, when the two charged parallel plates are connected to a voltage source, such as a battery, the two conductors will have equal magnitude of charge and opposite signs. So for instance, this particular uh, parallel plate will become positively charged, and that is denoted by capital plus Q. And the other plate will of course become negatively charged, denoted by negative capital Q. Okay, the distance between these two charged plates is considered very small. That is labeled by the letter D. Each plate also has a certain area. The area of plate A is equal to the area of plate B. So when we describe the area of a capacitor, we only are referring to the area of each of the plates. Now, since the two plates are charged oppositely, positive and negative, there is an electric field that is established in the region between the two charged plates. And this electric field is said to be directly proportional to the amount or magnitude of the charge in each conductor. So it follows, therefore, that the potential difference, labeled as V of AB, also known as voltage between the two charged plates, must also be directly proportional to the amount of charge Q. It simply means that if we double the amount of charge Q in this capacitor, we expect that the electric field will also double, and likewise, the potential difference between the two charge plates will also double. But the ratio of the charge to the amount of potential difference, or Q over V, known as the capacitance, always remains constant for any particular capacitor. Our first question is a conceptual question. The electric potential energy of a charged capacitor is stored in blank. Letter A, the positively charged plate. Letter B, the negatively charged plate. Letter C, the dielectric between the plates. And letter D, the electric field between the plates. So we say that a capacitor is actually a device that can store charges, and therefore it also stores electric potential energy. So where is the electric potential energy of a charged capacitor stored? Okay, so our answer is letter D. It is the electric field between the plates, okay, where the energy, electric potential of a charged capacitor is stored. Okay? This amount of electric field is directly proportional to the magnitude of the charge Q. And we also emphasize that the voltage, okay, the voltage between the point or the plates A and B is directly proportional to the value of the charge, but then the ratio Q over V, which is known as the capacitance, stays constant, okay, for whatever size or shape the capacitor may have. All right, so we also emphasize that capital C or capacitance is equal to the amount of charge Q divided by the amount of voltage. What is the SI unit of capacitance? If Q or charge Q is expressed in coulomb and the voltage V is in volt, then capacitance is expressed in a unit known as farad, capital F, in honor of Michael Faraday course. Okay. The scientist who put forward the principle of electromagnetic induction. We say that 1 farad is equivalent to 1 coulomb per volt. Please do not mistake the symbol for capacitance, capital C, with the symbol of the unit coulomb. Question number 2. If a capacitor 1 is equal to 4 microfarad and capacitor 2, which is equal to 8 microfarad, are connected in series, which has the greater amount of stored energy? Okay, that's the first question. And the second is, what if they are in parallel, which will have the greater amount of stored energy? So, before we look at the options, let's recall again the formulas related to capacitors when they are connected in parallel and when they are connected in series. So as shown in this diagram, to get the total or the equivalent capacitance for three capacitors C1, C2, and C3, when they are connected in parallel, we just add the individual capacitances. That means total C or equivalent C is equal to C1 plus C2 plus C3 plus C sub n, depending on how many capacitors there are. Say, for example, if there are n capacitors, all right? So this is the formula. When they're connected in series, okay, to get the equivalent capacitance or the total capacitance, we use the reciprocal formula. That means 1 over C is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over C of n. All right. So, we have the following choices. All right. So, when they are in series, which capacitor has the greater amount of stored energy? Is it letter A, C1, capacitor 1, the one with lower capacitance? And when they are in parallel, is it capacitor 2, the one with the greater capacitance? Or option B, the opposite. For series, it is C2, and for parallel, it is C1. Or is it letter C, the capacitance or the amount of stored energy is just the same whether they are connected in series or in parallel? So which among these three options is the correct answer? Here is the explanation. We say that in series, okay, the charge Q is constant. And since we have the formula that relates, okay, the amount of electric potential energy denoted by capital U, which is equal to the square of the charge Q squared divided by twice the capacitance. So in this is the formula for relating the electric potential energy, okay, with the charge Q and the capacitance C, whose charge Q is constant. So from this formula, it shows that the capacitor with the smaller capacitance should have the more stored energy. Okay, because if Q is constant, it follows that C is inversely proportional to U. All right. So the capacitor with the smaller capacitance gets the greater stored energy. That's for series. When they're in parallel, where the voltage or potential difference, capital V, is constant, the formula that relates the stored energy or electric potential energy U to the capacitance and to the voltage is in this formula. U equals 1/2 the product C and the square of the voltage. Okay? If V is constant, then it follows that C and U are directly proportional. So the capacitor with the larger C should have the greater amount of stored energy. All right. Therefore, our answer must be letter A. All right. Uh, Series, it should be the one with the smaller capacitance. When they are in parallel, it should be the one with the greater capacitance. Okay. So we also emphasize this relationship of stored energy or electric potential energy stored, okay, in terms of the charge Q, capacitance, and the voltage V, depending on whether the capacitors are connected in series or in parallel. Or generally, okay, this one here, 1/2 QV, this is the general relationship, okay, between electric potential energy stored, the charge Q, as well as the voltage V. Why do you think there is a 1/2, constant 1/2? This 1/2 refers to the average amount of potential difference, okay, in a given conductor. Okay, at the start of charging a capacitor, where the initial voltage is 0, as the charging process continues, okay, the amount of voltage increases, okay, linearly with the amount of charge that is being stored in the capacitor or in the plates. All right, so uh, when the capacitor is fully charged, okay, we we refer to the average. All right, we refer to the average amount of voltage, and the initial amount of voltage being 0 plus the maximum voltage, which is V. Their average, of course, is equal to 1/2 of the total voltage V, and hence this formula, 1/2 Q times V. Question number 3. A power plate capacitor has a capacitance of capital C. If the area of the plates is double and the distance between the plates is half, what is the new capacitance? Choices are A, C over 4, letter B, C over 2, letter C, 2 or twice C, and letter D, 4 times C. Correct answer must be letter D, right? We have the formula for relating the capacitance of a given capacitor in terms of the following quantities. K here refers to the constant, dielectric constant, uh, which refers to the, what we call this, the constant of proportionality of the insulating material between the two charged plates. Okay. Normally, when there is no insulating material, we assume that the charged plates are separated by nothing, or in short, in a vacuum. Okay, where the value of K is equal to exactly 1. The unit of K, or there is no unit for this constant K. The value of K for air is almost equal to 1. It's something like 1.00006, something like that. All right. So practically, when air is the insulating, what you call dielectric, that is almost the same as having the capacitor in a vacuum. Now, this other constant, we call this the permittivity of free space. That is a universal constant, which is equal to 8.85 raised to the negative 12 farad per meter. This is epsilon naught, the symbol for permittivity of free space. Capital A represents the area of each plate of a capacitor. Okay, so in considering the area, we only are referring to the area of one charged plate. We do not double or we do not add the areas of the two plates. It's just the area of each plate. Then that is divided by the distance d that separates the two plates. All right, so why is our answer letter D? So if all the constants are considered and we just uh, look at the way the areas or the area of the capacitor is changed, it says that the area is doubled. So what we do is we multiply to get the new capacitance C2, we just multiply the area A1 by 2. And at the same time, the distance between the plate, when it is half, so what we do is divide 0.5, the product, the value of the original distance D. That's the same as having 1 half multiplied by D1, 0.5 D1. Okay, so that will give us for the new capacitance C2 being equal to 4 times the original capacitance C1. Therefore, that makes letter D our answer to this question. Question number 4. A capacitor has vacuum in the space between the conductors. If you double the amount of charge on each conductor, what happens to the capacitance? Letter A, it increases. Letter B, it remains the same. Letter C, it decreases. Or letter D, it depends on the size and shape of the conductors. Okay, the best answer, of course, is letter B. Okay, the capacitance does not depend on the value of the charge Q. This was emphasized earlier. So, doubling the charge Q causes the potential difference V to double. So the capacitance in the formula C equals Q over V, okay, the capacitance remains the same. When you double Q, the denominator also doubles. So it's just as if nothing happens to the value of the capacitance. Okay, and this is true regardless of the size and shapes of the conductors. Take note, always remember, okay, the amount of charge does not affect, okay, the value of the capacitance for a given capacitor. Question number 5 is a problem-solving question. The plates of a parallel plate capacitor in vacuum are 4.00 millimeters apart and 1.50 meters squared in area. A 5.00 kilovolts potential difference is applied across the capacitor. Compute letter A, the capacitance, letter B, the charge on each plate, and letter C, the magnitude of the electric field between the plates. Alright, so our solution for letter A, the capacitance, we use the formula C is equal to epsilon naught multiplied by A over D. Okay, supposedly there should be a constant K, the dielectric constant, but that dielectric constant, when the capacitor is in a vacuum, is understood to be 1. Alright, so we don't include that here anymore. So substituting our permittivity of free space, the universal constant is there, 8.85 raised to the negative 12 farad per meter multiplied by the given area of uh, a capacitor, which is in meters squared, of course, is 1.50 meters squared, and that is to be divided by the separation distance of the two plates, which when converted from millimeter to meter becomes 4.00 raised to the negative 3 meters. Okay, so doing your math, we will get this value for capacitance equal to 3.34 times 10 to the negative 9 farad. So that's our answer for letter A. Moving on to letter B. Okay. To get the charge on each plate, we use the formula Q is equal to the product of capacitance C multiplied by the potential difference capital V. Substituting, we get 3.34 raised to the negative 9 farad multiplied by the given voltage already converted to volts. From 5 kilovolts, it now becomes 5.00 raised to the third power volts. So multiplying this, you will get 16.7 raised to the negative 6 coulomb. And since we are asked, okay, to find the charge on each plate, we have on the positive plate, the charge is positive 16.7 raised to the negative 6 coulomb, while on the negative plate, we have negative 16.7 raised to the negative 6 coulomb. And finally, for our last question, letter C, what is the magnitude of the electric field between the plates? Okay, we can use this formula that relates electric field to the amount of charge Q and to the permittivity of free space, universal constant, as well as the area of each plate. All right, so this is the formula for that. And substituting, we already have our value for Q, 16.7 raised to the negative 6 coulomb divided by that constant. Before dividing, all right, before dividing the value of Q, we should first get the product of the constant epsilon naught by the area. Okay, the moment we have that product, then that's the time we divide 16.7 to the negative 6 coulomb by that product, and we will get the result, electric field being equal to 1.26 times 10 to the 6 Newton per coulomb. Okay, we can check this electric field using another formula, okay, and that is in terms of the voltage V and the separation distance D. We just divide voltage divided by D. Okay, substituting for our voltage 5.00 to the third volts divided by the distance separation in meter, 4.00 raised to the negative 3 meter, we will get the result, which is 1.26 to the 6 power volt per meter, which is actually also is equal to Newton per coulomb. Question number 6. How should you connect a 3 microfarad capacitor and a 6 microfarad capacitor so that the 3 microfarad has a greater potential difference across it compared to the 6 microfarad capacitor? Letter B, how should you connect them so that the 3 microfarad capacitor has a greater charge than the 6 microfarad capacitor? Okay, the choices are letter A, series, letter B, parallel, letter C, either series or parallel, and letter D, neither series nor parallel. So these options, A, B, C, and D, are for both question A as well as question B. All right, so the answer is, let's first go to the explanation. Okay, we say that in a series connection, the two capacitors carry the same charge Q. All right, so in series, the charge Q is always constant, but they have different potential difference. And this potential difference is described as V is equal to Q over C, right? The capacitor with the smaller capacitance will have the greater potential difference, okay? Because they are inversely proportional. V is inversely proportional to C, okay, if the Q is constant, and that is when the two capacitors are connected in series, right? The one with the smaller capacitance C has the greater potential difference. That's why our answer for question letter A is series, or letter A. Now, if they are connected in parallel, the two capacitors have the same voltage, potential difference V, but they carry different charges since they are in parallel. And this charge, okay, the charge carried by each capacitor is expressed as Q is equal to the product of C times the voltage. And since V is constant, or voltage V is constant, it follows that the capacitor with the larger capacitance C has the greater amount of charge. Okay? Uh, okay, careful analysis would tell us that the 3 microfarad capacitor, or the one in smaller amount of capacitance, can never be or can never have greater Q, okay, than the 6 microfarad, whether they are connected in series or in parallel. Okay, it is always the greater the capacitor with the greater capacitance that shall have the greater amount of charge Q, okay, based on this formula. That's why our answer for letter B is option letter D, neither series nor parallel, because it is always the capacitor with the greater capacitance that will carry the greater amount of charge Q. Question number 7. The space between the plates of an isolated parallel plate capacitor is filled by a slab of dielectric with dielectric constant K. The two plates of the capacitors have charges positive Q and negative Q. You pull out the dielectric slab. If the charges do not change, how does the energy in the capacitor change when you remove the slab? Letter A, the energy increases. Letter B, it decreases. And letter C, the energy remains the same. So our answer, since the charge Q remains the same, that's stated here, all right? The stored energy from the formula U is equal to Q squared over 2C, all right? Removing the dielectric will lower the capacitance by a factor 1 over K. And from that formula, since U is inversely proportional to capacitance, okay, the stored energy, it follows, shall increase. Okay, stored energy, capital U, increases by the same or by a factor K at constant Q. Okay, C is inversely proportional to U. So our answer, as shown, is letter A. The energy stored increases, in fact, by a factor K. Now, uh, we can also explain this in terms of the law of conservation of energy. Okay? When you pull the dielectric slab out of the capacitor, okay, there is a resistance, something like the electric field is trying to prevent you from doing that action of removing the slab. Okay? So you are going to experience a force, a resisting force coming from the electric field. But since you're going to try to overcome such force, then you have to do work. Okay? And the amount of work that you do on the system, okay, is in fact converted into an increase in the stored electric potential energy stored in fact in the electric field of the capacitor. So it again shows that energy cannot be created out of nothing. Okay, you want to store energy in the capacitor. Okay, one way is by removing the dielectric slab away from that what we call electric field between the two plates. But in doing so, you have to do work. And the amount of work that you do, in fact, becomes the energy that is stored in the capacitor. Our last question, number 8, is again a problem-solving question. For the system of capacitors shown in the figure here, a potential difference of 25 volts is maintained across AB, all right, across point A, B. Question letter A, what is the equivalent capacitance of this system between points A and B? Letter B question, how much charge is stored by the system? Letter C, how much charge does the 6.5 nanofarad capacitor store? And letter D, what is the potential difference across the 7.5 nanofarad capacitor? All right, so looking carefully at the diagram, okay, we have how many? 1, 2, 3, 4. There are 5 capacitors, okay, connected. The 3 of them, the ones inside, are connected in series. Okay, the 18 nanofarad and the 30 nanofarad and the 10 nanofarad are all connected in series. Okay, so if you're going to get the combination capacitance for these three, if they are in series, okay, we will apply the formula for adding or getting the total capacitance in series, which is the reciprocal formula. Okay, and the sum, whatever is the sum, will now be considered parallel to both 7.5 nanofarad capacitor and to the 6.5 nanofarad capacitor. So our last combination, therefore, will represent the combined capacitance of these three parallel capacitors. So we shall start answering letter A. Okay, we first get the total capacitance of the ones inside, okay, using the reciprocal formula, which is 1 over C is equal to 1 over 18 plus 1 over 30 plus 1 over 10 nanofarad. All right? That's our substitution in the reciprocal formula. And then getting the, what do you call this, the common denominator. One common denominator would be 180 C. Okay, 180C when multiplied to each term in the equation will give us 180C divided by C, of course, is 180. That's on the left side of the equation. Is equal to 180 divided by 18 times 1 will give us 10C. And 180C divided by 30 multiplied by 1 will give us 6C. And 180C, okay, multiplied to 1 over 10 will give us 18C. And then adding these terms and solving for C, we will get 5.30 nanofarads. Right? So this is the equivalent capacitor or capacitance of those three capacitors inside, which I said earlier, okay, is parallel to 7.5 and to 6.5 nanofarad capacitor. So to get the sum of the capacitors or capacitance in parallel, we just add them directly, meaning 7.5 nanofarad plus 6.5 nanofarad plus 5.3 nanofarad will give us 19.3 nanofarads, all right, as the combined capacitance or equivalent capacitance for the whole system between points A and B. All right. Okay, we shall look at our solution for letter B in the next slide. Alright, moving on with our solution, we are now going to answer question letter B. How much charge is stored by this system? Alright, so we just use the formula. Total charge QT is equal to the product of the voltage times the total capacitance. Okay, since the total voltage in the system, that is across A and B, is given 25 volts, multiply that by the amount of capacitance total or equivalent capacitance we had earlier, which is 19.3 raised to the negative 9 farad. All right. So in other words, when combining with volts, the nanofarad has been converted now to farad, and 1 farad is in fact equal to 10 to the 9 nanofarads, or 1 nanofarad is equal to 10 to the negative 9 farad. So multiplying by 25, this gives us 4.8 raised to the negative 7 power. Okay, the unit is coulomb. When you multiply volt times farad, the result is a unit of charge, which is coulomb. All right. So that is the answer to question letter B. For letter C, how much charge does the 6.5 nanofarad capacitor store? 6.5 nanofarad is this one here. All right. All right. 6.5 nanofarad capacitor is parallel to 7.5 nanofarad and to the combination of these three inside. All right. So to get or to describe how much charge does the 6.5 nanofarad capacitor store, we just use again the formula for finding Q, which is the product of voltage times C, right? Since in a parallel combination of capacitors, the voltage across each capacitor is the same or constant, so all we need to do is multiply that constant voltage, 25 volts, by the given capacitance, which is 6.5 raised to the negative 9 farad, and we get the value for Q equals 1.6 raised to the negative 7 coulomb. This is the charge stored in the 6.5 nanofarad capacitor. And finally, for letter D, what is the potential difference across the 7.5 nanofarad capacitor? Right. So our answer for this question doesn't require any computation, because we say that the 7.5 nanofarad capacitor is in parallel. All right. Parallel, connected in parallel to the voltage source across point A and B, whose voltage or potential difference across is 25 volts. So it follows that the voltage across this capacitor 7.5 nanofarad is also equal to 25 volts, where we say that the voltage is just equal to the individual. The total voltage in the whole system is just equal to the individual voltages across each capacitor connected in parallel. So that is all for this video tutorial. Thank you very much.